Welcome back once again. My name is Richard. It has never changed. Today we are tackling gas phase of the MCAT General Chemistry review. Without wasting any time, let's move on straight to the point. Imagine you have a helium balloon and you tie this helium balloon to your car's gear, the shifting gear or the handbrake in the car, and you suddenly move the car forward. What do you expect would happen to the helium balloon? Now, the common sense is that the helium balloon would jerk backwards, just like you, when you first move your car, you jerk back because of inertia. But no, the helium balloon would not do that. The helium balloon will move forward instead. Now, you might ask, why would the balloon move forward instead of moving back? It's because the average molar mass of a helium balloon is like 4 grams per mole, right? And the air around it, the average molar mass of the air around it, which is mostly nitrogen and oxygen, is around somewhere, 28 grams per mole. So it is way heavier than helium. So helium would float. So when you have the car, let's say this is our car, right? And then you move the car forward. Since the air is also heavy, the air will jerk back with you. So there will be more air pressure at the back of the car than there is at the front of the car. But since the helium mass is almost negligible, it doesn't jerk back. The pressure difference between the air pressure at the back of the car and the front of the car would exert a pushing force on the helium balloon, which is over here, and it will push the balloon forward. That is why the balloon will move forward. Who knows science could be this fun? That brings us to gas phase. When we talk about gas phase, it is nothing mysterious. When we was dealing with states and state functions and all of that and changing state from one form to another, gas phase is just a phase of a matter, or it's a phase of a system too. So, and as a phase of a system, it has its state properties, just like any state. The state properties that we was doing, it has it too, just like every other system. But this time it is a new phase. And that phase, the only difference between a liquid and a gaseous state is that the gas molecules, they are very spread out apart, so much so that the intermolecular force of attraction that exists between them is negligible, but it's never zero. But for the sake of gas phase, we're going to consider that the intermolecular force that exists between the gaseous molecules is negligible. That is one. And then also the particles flows, fast enough. So the state functions that would define the gas phase is that we're going to work about. That is going to be the whole chapter, the whole discussion of this entire topic is one. We have pressure. We have volume, right? We have temperature. And then let's add amount of substance, which is mole, to it. So these things, right, are the state functions that governs gaseous phase over here. Now the pressure over here, and then the volume, and then the temperature, and then the mole, we're going to talk about it. But for us to, describe a gas at this phase, we need to find, or we need to hypothetically create a gas that we are going to talk about. And that gas that we're going to create or talk about is called ideal gas. I hope you've heard this so many times in your search or in your learning through the MCAT or chemistry. But basically what ideal gas is a gas whose molecules have negligible volume. Means the volume that the molecules occupy is almost zero. And for that matter, since they occupy almost zero, we also say that the intermolecular forces of attraction between them is also almost zero. So the gas occupy no volume and there's no intermolecular force of attraction. That is ideal. In fact, no gas in the world behave like this. That's why we call it ideal. Now, let's move away from the ideal gas because that is going to be our gas. And let's talk about STP, which is standard temperature and pressure. Now, standard temperature and pressure is also the temperature and pressure that is governing our ideal gas over here. Do not confuse standard temperature and pressure with standard conditions or standard state conditions. The standard temperature and pressure are different from standard state conditions, such that in standard temperature and pressure, we say the pressure over here is 1. Let me make it this cool so that you could understand what I'm trying to write and not just mambo jumbo on the board. Okay, so this is STP, standard temperature and pressure, and SSC, standard state conditions. This STP is basically used for gases, right? And then this SCC is basically used when we are doing thermodynamics, right? When we are doing like thermodynamics or thermochemistry, right? For pressure, let me also put pressure over here. If we are talking about pressure under standard conditions, we usually use 1 atmosphere. 1 atmosphere, which is also equals to 760 torr, or 760 millimeters of mercury, or 101.3 kilopascal, right? I think, is it Pascal? Is it PA? Yeah, kilopascal. So when we talk about standard conditions, the pressure is 1 atmosphere, 760 torr, or 760 millimeters of mercury, or 101.3 kilopascal. You can also convert this, or you can run the 101 to just 100. Under standard conditions or standard state conditions, the pressure is the same. The pressure would go same, 1 atmosphere, or 760 torr, or 760 millimeters of mercury, or 101.3 kilopascal. So the pressure is the same whether we are dealing with standard temperature and pressure or standard state conditions. That is one. The second one we are going to talk about over here is temperature. Now this is where it gets interesting, right? Temperature under standard temperature and pressure, STP, is 0 degrees Celsius. 0 degrees Celsius. Why is my marker acting like this? Let me get a new one. It's 0 degrees Celsius, or is 0 degrees Celsius, or 273 degree Kelvin. Now, to convert degree Celsius to degree Kelvin is basically the degree Celsius plus 273 would give you the degree Kelvin over here. And then under standard state conditions, the temperature, we started at 25 degrees Celsius, which is room temperature. Now, 25 degrees Celsius is going to give us 298 Kelvin. So the temperature changes. The temperature for standard temperature and pressure is 273 Kelvin, or 0 degrees Celsius. But for SSC, it is 25 Kelvin. It's 25 degrees Celsius, or 298 Kelvin. And if we talk about volume, under standard state conditions, we don't define volume. Under standard temperature and pressure, if the gas is ideal, if and only if the gas is ideal, will the volume be 22.4 decimeter cube, or 22.4 liters, or 22.4 liters. Only, asterisk, only if gas is ideal. Only if the gas is ideal, but we do not define the volume for the SSC because it can occupy any volume. And when we talk about moles over here, Or let's talk about concentration, because the moles is also not defined. Talk about concentration. The concentration for STP is not defined. We don't really define it. But the concentration for SSC, standard state condition, is 1 molality, like one molality is also 1 mole per liter. Liters is also decimeter cube. So this is the difference between standard state pressure and standard temperature and pressure, and then standard state conditions. Once that is set, we move on to pressure. Now, talking about gas phase, right? When we're talking about pressure, there is the unit or the instrument used to measure a pressure is the barometer, right? The barometer is used to measure pressure. Now, when you go into like clinical operations, like you go to the hospitals or nurses, their barometer is what we call the sphygmomanometer. Sphygmomanometer. Yeah, it's called the sphygmomanometer. Now, how does like a normal barometer works, and why do we measure it in millimeters of mercury over here? It might be relevant in a MCAT, so let me just brush it off like in a tiny bit. Imagine you have a tube, right? And then this tube is filled with mercury too. Let's say over here, it's filled with mercury. Over here is mercury, which the chemical name or the whatever name is hydrogen. That's why we call it Hg. Hydrogen is mercury. So it is millimeters of hydrogen, essentially millimeters of mercury. So we have this tube of mercury, we put it in a basin, right? And then this basin is also filled with mercury. Say mercury, nothing else. Now the forces acting on this mercury is one, the atmospheric pressure, which is what? 1 atmosphere. The atmospheric pressure acts this way. So over here is the atmospheric pressure. Now, if the atmospheric pressure acts downwards, the weight of the mercury, this is why we use mercury, because mercury is a liquid metal. It is also heavy. So that is why we use it, because you can actually measure its weight and it doesn't really, freezes or solidify conforming to extreme temperatures, right? So the weight of the mercury is also going to act down. This is the weight. Weight is mass times gravity. It's going to act down. Now you might say, since the air pressure is acting down and then the weight of the mercury is also acting down, you might think that they are all acting down, but no. If you think about it, the weight, like, it's just gravity pushing down the mercury. So if it pushes it down from the tube, it will come into the basin over here. Let's say if this is the level of the mercury, it will come into the basin and it will displace the weight up. So in actual sense, the atmospheric pressure is counteracting the weight of the mercury. The weight of the mercury. So in clinical, like if the atmospheric pressure, is greater than the weight of the mercury, right? Then it is going to push down, more mercury is going to flow into the tube, and the level of the mercury is going to rise. So if the atmospheric pressure is greater than the weight of the mercury, we have a rise in the level of mercury in the tube. Now, if the atmospheric pressure is less than the weight of the mercury, we have a fall. The mercury pressure would fall. So due to keep it going. Yeah. It's covering the hole. Okay. So due to the rise and then the fall of the mercury, we can Due to the rise and fall of the mercury, we can determine a change in height difference, and that height difference is measured in millimeters. So that is why we have the millimeters of mercury, like how many millimeters did the mercury move. So if we have a pressure like a regular heart rate, which is 120 over 80, so it's 120 millimeters of mercury over 80 millimeters of mercury. So this means the mercury moved 120 millimeters. Over here, it moved 80 millimeters. That's basically what it is. Now, this is the same concept used in a sphygmomanometer, which is the blood pressure cuff that they use in a hospital. The only difference is that this atmospheric pressure is substituted. It changed the atmospheric pressure to the person's blood pressure, the pressure that is exerting on the veins and the arteries. This atmospheric pressure is replaced by that. Hence, we could determine a person's blood pressure in that way. So that is another useful forms of like a pressure, and then gases as we are talking about them. Now, since we started with the ideal gas, let me clean over here. My board is too small. If you guys want to donate so I could get a bigger board and put it in my living room, that would be really great. Now, since we started with the ideal gas, right? The ideal gas. So the ideal gas is a gas that do not has any volume. So the volume equals to 0 because the particles are too small. They don't occupy any volume. And then the intermolecular forces is also negligible. Due to this, scientists perform like a series of experiments to determine to relate the properties that we listed. Then the properties were pressure, again, volume, again, temperature, and then again, moles. So scientists did a series of experiments to find a relationship between these state functions of the gas phase. And they found out that, and this equation is one of the most popular equation in the whole of chemistry, is PV equals to nRT. Now PV, so the pressure, where P is the pressure, V is the volume, the N is the moles, R is the gas constant, and T is the temperature. Now you can have R, right, as 8.2 times 10 raised to the power, let me see, 8.2 times 10 raised to the power negative 2 latest atmospheres, all divided by Kelvin, right, all divided by mole dot Kelvin. You can have R in this form, or you can have R as 8.3. Oh, I actually know this. 8.3 joules per Kelvin per mole. Now, watch something interesting here. The R is the gas constant, and it comes in two forms. You see that 8.2 times 10 raised to the power negative 2 latest of dot atmospheres divided by mole per Kelvin, or we could have it as 8.314 joules per Kelvin per mole over here. Don't get it a little bit confused, because this function over here, this latest is what? Volume, right? And then atmosphere is pressure, right? And work done over here is equals to the pressure change in volume, or pressure times volume. So we could replace up here with work done, and work done is measured in what? Joules. That is why this unit became joule per Kelvin per mole. Nothing mysterious, just change of functions. and a little bit. So I'm going to write all the equations we are going to encounter in this gas phase over here, because it has like a lot of equations. So the first one is PV equals nRT. That is posted over there. We have it written there. Don't get it twisted. Now, as we move on, if we are supposed to go into details and plot a graph of pressure versus volume on a graph with the increasing or decreasing temperatures, we are going to get some graph that looks like something like this. But you should know instinctively that, the relationship between pressure and then volume, which we will cover still in this chapter. So let's move on a little bit. This ideal gas law over here, we could use it to calculate two more things. We could use this ideal gas or the ideal gas law to calculate one, the density of the gas we are talking about, the density of the gas we are talking about. How do we define density? Now, density is the mass per unit volume of the gas. So density is equals to M over V, like this over here. So if I decide to make V the subject, I will get my density to be, if I make V the subject, I'll get V is equals to M divided by the density, like that, because you would cross multiply, becomes PV equals to M, and then you divide it by the rho, which would give you this. If I call this equation 2, and if I call this equation 1, and I'll put equation 2 into equation 1, I'm going to have pressure times the pressure times the volume, which is mass over the density, equals nRT over here, nRT. And over here, if I want to make density the subject, I'm going to have the density to be equals to pressure times mass divided by nRT. So I could have this over here, and if I have just 1 mole of gas, this will just be PM divided by RT, like that. So if we try to use density, that is the equation that we do get. So the equation involving density is equals to the pressure times the mass divided by moles times the gas constant times the temperature. Now that is done. The second thing that we could use the ideal gas law to calculate is also the molar mass of the gas. So the molar mass, right? The molar mass is equals to the mass of the gas divided by the number of moles. So divided by moles over here, which is big M, equals to mass, right? Small m divided by n. Cool over here. If I decide to make moles the subject, I'm going to have the moles giving me small m over big M. If I decide to put this equation into our almighty ideal gas equation, I'm going to have PV equals to N, which is now mass over molar mass, small m over the big M, like this. And then I'm going to have the RT over here. If I want to make the molar mass the subject, it's going to be the molar mass equals M, which is mass, R, which is the gas constant, T, which is temperature, divided by the pressure and then the volume over here. So this is also the third equation that we could find. 3, which is the molar mass, big M, equals to MRT divided by PV. that is set and standard. So from the molar mass, we also have the Avogadro's principle. Anytime we hear Avogadro's principle, what should pop into your head is moles, because that bro really love moles. So 2 was the molar mass, and then the 3 is Avogadro's principle. Let me get it and then go straight to Avogadro's principle. Avogadro's principle. So around the time in the 18s, I think 1888 or thereabout, this guy, Amedio Carlos Avogadro, also because a lot of people were working on gases, he decided to work on gases with his moles. And he made a principle which states that under isothermic, that is constant temperature, and then isobaric condition, under isothermic and isovolumetric conditions, means under constant temperature and volume, under constant temperature and constant volume, cut that part. So the Avogadro's principle stated that under constant temperature, so under constant temperature, and if the temperature is not changing, we'll call it what? Isothermic. So under isothermic and constant pressure, if pressure is also not changing, what do we call it? Isobaric. So under isothermic and isobaric conditions, the volume, the moles of a gas is directly proportional to the volume it occupies. So the moles of gas is directly proportional to the volume. That is literally the Avogadro's principle. So under constant temperature and pressure, the moles of a gas is directly proportional to the volume it occupies. So if you want to turn this into an equation, you say number of moles directly proportional to volume. If we want to change the proportionality sign and replace it with an equal sign, we need to introduce a constant. So K becomes my constant. So over here, if I have like 2 gases, right? Let's say this is gas 1, which I'm going to have N1, K1, V1 over here. And then I want to make K the subject. So K1 equals to N1 over V1, like this. And if I have, let's say I have 2 gases under the same constant temperature and pressure, and these 2 gases are ideal, K is going to be the same. So I'm going to have K2, which is also equals to N2 over V2. But K1 would be equals to K2 under constant temperature and pressure, because they are all in the same condition. You understand me? So I can equate these two and have N1 over V1 equals N2 over V2. So this is just the relationship that exists between the number of moles and then the volume. If we have that, understand, I'll add that to our equation. So that will be equation 4. That goes N1 over V1 equals to N2 over V2. So, let's do something. Let's make here, this is our ideal gas law. This is respect to density. And this is respect to molar mass. And then this is the Avogadro's principle. Principe. So from the Avogadro's principle, as I said earlier, a lot of scientists were working on gases at that time. We can move to this our infamous scientist Mr. Boyle. So Boyle over here was also doing experiments on gases comparing pressure and volume. So Avogadro compared moles and volume. Boyle comparing pressure and volume. So Boyle says under constant temperature, hold on a minute. Yes. So Boyle says under constant temperature, which is isothermic conditions, the pressure of a gas is inversely proportional to the volume. Now, this thing should be instinctive. Let's say I have a canister of gas, right? Take this to be my canister of gas, right? There is some gas over here. If I apply more pressure, if I put more pressure into this canister, the gas is going to be forced to occupy a small volume over here. So it means the higher pressure I occupy, the smaller volume the gas would fill. But if I lower the pressure, like I'm no longer applying as much pressure, the gas is going to spread out. So less pressure, more spreading. And that's literally Boyle over there. So all these things, this is a little bit of a commonsensical. So he was also saying that pressure is inversely proportional to volume. Same way, under isothermic conditions, right? So if I want to change the proportionality sign, I get this K over V, right? So if I have two gases, which is K1 and K2 gas, or which is gas A and gas B, I'm literally going to have, if I make K the subject over here, I'm literally going to have K1 equals P1 V1. And if it is two gases, I'm going to have K2 equals P2 V2. But K1 is equals to K2. I can now relate P1 V1 equals P2 V2. You get your Boyle's law. So over here now, equation 5, we have the Boyle's law that states P1 V1 equals P2 V2. Okay, so once we are done with Boyle, we can move on to a different scientist, Charles and Mr. Gay-Lussac. Who should I clean? I'm gonna clean Avogadro. Okay. So I will make this Avogadro. I'll make this Boyle's. This is Boyle's law. So after Boyle's law, let's move on to Mr. Charles. So what did Boyle do? Boyle compared pressure and then volume. Now Mr. Charles compared volume and temperature. And then let's make let's build a point here. We said that temperature, right? Temperature over here is proportional to the absolute thermodynamic, is proportional to the average molecule, the movement of the molecules. So the temperature is proportional to the kinetic energy. We said that. We know that the kinetic energy is equals to, so kinetic energy is equals to half mv square, right? The moment we introduce temperature into it, the kinetic energy is going to be, introduce temperature into it, the kinetic energy is going to be 3 over 2 kBT, where this kB is the Boltzmann constant. We will get there, right? But I'm not going to add it to this equation yet. I just wanted to show you that the temperature is equivalent to the average kinetic speed, right, of the average speed of the molecules moving. That is literally the temperature. So Charles said that under constant pressure, under isobaric conditions, the temperature is directly proportional to the volume, because the same thing, if I have my gas canister over here and the gas is over here, if I increase the temperature, the gas are going to gain more kinetic energy and hence move more faster and spread more out. So higher temperature, higher volume. Mr. Charles over here said that under isobaric conditions, temperature, or let me just go, volume is directly proportional to temperature under isobaric. What is isobaric? Constant pressure. Same way, it all follow the same situation. If I want to change this proportionality sign to equal sign, I have to introduce a constant. And if I have two gases, right, which is, say this is gas 1 and gas 2 over here, if they are all under the same conditions, isobaric, the constant of proportionality will be the same. So if this is V1, K1, T1, this will going to be V2 equals to K2, T2. And their constants of proportionality, which is Kk, are going to be the same. If I want to make K the subject over here, this K1 is equals to V1 over T1. And then this K2 is also equals to V2 over T2. So if I want to if they are under the same isobaric conditions, the constant of proportionality are equal. So K1 equals to K2. Therefore, V1 over T1 is equals to V2 over T2. Simple like this. Now, if you want to make it like a little bit simpler so that you have a linear equation, you could also do it like this way. Cross multiply, which is V1 T2 equals to V2 T1. You could do it like this. If this would confuse you, you could use this one. Same situation. So let's add it to our chain of equations that we are just pulling out for this guy's face. So our equation number 6 is V1 over T1 equals to V2 over T2, or we could write it as V1 T2 equals V2 T1. And what is that? That is the Charles law. And you know something that is funny? There is a guy who was working around the same time that Mr. Charles was doing this. His name was called Mr. Gay Lussac. He wasn't gay. I don't know if he was gay or not, but hey, can't judge, bro. Why are you gay? But I can't judge. Mr. Gay Lussac was also doing a similar experiment, but what was he doing? He was comparing the pressure and the temperature. So what did First of all, what did Avogadro do? Avogadro compared moles and volume. Ball compared pressure and volume. Charles compared volume and temperature. So it seems volume is all constants through here. But somebody who refused to use volume in his experiment is Mr. Gay Lussac. Is that why his name is Gay? Because he refused to use volume? Is he gay? Nah, I don't know, man. But why are you gay? Okay, let's move on. Now, Mr. Gay Lussac also did an experiment to compare I'm laughing like killer. So Mr. Gay Lussac also did experiment to compare pressure and then temperature. So these experiments that these people were pulling out from, I don't know, from their asses, couldn't be their asses, back in the 60s, all simple common sense, right? It wouldn't take a genius to figure this out. I'm sorry. Hey, I'm not blowing my own trumpet or nobody's trumpet. In fact, I cannot blow my own trumpet. Bass, my G. Bass. So, I was still talking. So, Mr. Gay Lussac said that if you have a gas in a canister one more time, right, and then you increase the pressure, you reduce the temperature. The temperature will become low. Now you might think that, if I increase the pressure of something, wouldn't the temperature increase? No, bro. We said the temperature is equivalent to the speed, the movement of these particles. So if I have a gas in this canister and I increase the pressure over here, wouldn't the molecules limit, wouldn't the space which they can move limit, and thereby limiting the space they couldn't move, so that they would just be occupying a smaller space? And if I reduce the pressure, they can now move faster. So pressure is inversely proportional to volume. And they all follow the same similar pattern too. Pressure is inversely proportional to the volume, as in a sense that pressure is inversely, temperature. We're comparing pressure and temperature. It's inversely proportional to temperature. So over here we could get P1 T1 equals to P2 T2. I'm not going to go through that whole process again. You know that already. So our equation 7 is going to be P1 V1, or P1 over T1 equals to P2 over T2. Or we could write it as P1 T2 equals P2 T1. And who was that? Mr. Gay-Lussac. Please, I didn't say he was gay. I was just asking a question. Okay, so after that, after all these things, we can now link all of these, the 5, 6, 7, which is Boyle's, Charles, and then Gay-Lussac law, to what we call the combined gas law. Now, the combined gas law goes like this. Hold on, where is it at? I think it's going to be P1 V1 T1 equals to P2 V2 T2. But let me look at it. Yes, we can combine all these gas, relate all of these equations to the combined gas law. So the combined gas law is going to be P1 V1 all over T1 equals to P2 V2 all over T2. Simple as that. This one over here is our combined gas law. So our equation number 8 is going to be the combined gas law, which is P1 V1 T1 equals to P2 V2 T2. That is the combined gas law. Once that is succeeded, we can move on from here and now move to, we can now move to the Dalton's law of partial pressure. I will clean over here. We're still dealing with ideal gas. I'm confused that. So the Dalton's law of partial pressure states that if you have a cylinder, or like a system that has multiple gases in it, and these gases do not react with each other, right? The total pressure of the gas is equal to the sum of the individual gases, the sum of the pressure of the individual gases in it. So if you have Dalton's law of partial pressure, Dalton's law of partial pressure. So if you have like your canister, one more time, we're never going to get rid of this canister. And you have, say, gas A, gas B, gas C, gas D, gas E, blah, blah, blah. A lot of gases in this. And these gases do not react with each other. And you want to know the total pressure, that is, the gases in this are certain, is equal to the sum of the individual pressure. So the pressure total is equals to the pressure of gas A plus pressure of gas B plus pressure of gas C plus pressure of gas D, all the way to the pressure of gas infinity, however many gases you do have. Now, and then if you are attempt to find only the pressure of gas A, right, the equation that you can use to find the pressure of gas A is going to be the moles. Let's X represent the moles of gas A times the total pressure. This is simple and basic algebraic mathematics over here. So our equation number 9 would be this full combined pressure, and then our equation number 10 would be this, the pressure of the individual components of the gases. Literally Dalton's law of partial pressure. Once again, it says that if I have a cylinder that has a lot of gases in it, if I want to calculate the total pressure, it's the sum of the individual pressure. Simple enough. How do I find just individual pressure? You can find the individual pressure by multiplying the mole amount times the total partial pressure. So that is gone. Okay, maybe one more thing. You could also say, how do you find XA, which is the mole of gas A? So the mole of gas A is literally where this is going to be the moles of gas A, all divided by the total moles. So literally this XA is the mole ratio. Forgive my tongue. The mole ratio times the total pressure would give you the pressure of gas A. We can move away from that and go straight to Mr. Henry's law. There are a lot of laws when it came to gases, a lot of formulas, a lot of hula balloons. I don't know what that word means. Oh, God. So let's go to Henry's law. What did Henry do? Well, let's go ask Henry. So Henry's law was just about solubility of gases in solutions. And if we talk about the solubility of gases, how gases is going to dissolve or become part of a solution, we are literally talking about the concentration. Solubility is equivalent to concentration in this gas phase. We're going to, talk about it a lot. But say one more thing. Let me bring your mind back before we move forward from here. And this will make a bridge between one or two things. Once again, if I have this canister one more time, or not even this canister, let's say I have like a pot, right? And then I apply fire into the pot, and then I cover the pot. And then the pot has water in it, right? Now, once it reaches this boiling point, we know that evaporation occurs at the surface of the water, and then the vaporization is through the entire thing. So when the water reaches boiling point and some of the particles break into gases, right, there is going to be a vapor pressure. And this vapor pressure is literally the gas that have, the molecules of the water that have broken into the gaseous phase. These molecules would exert a pressure on the water, and it would force some of the gases to turn into water. That pressure over here is called vapor pressure, like I just said. Vapor pressure. Now, vapor pressure is the only reason why liquids boil. It's not because you are putting a lot of fire into it. That is not why liquids boil. Liquids boil, the vapor pressure. Liquids boil when the vapor pressure is equal to the atmospheric pressure. Just like that. That is how liquid boils. So, and this vapor pressure, atmospheric pressure, converting back will take us back to equilibrium to establish equilibrium in concentrations and all that. We did that in the chapter 7 of the MCAT Chemistry review. You can go watch that video. But we are basically stating that when it comes to the Henry's law, we are basically stating that the solubility of a gas is equals to KH. The KH here is the Henry's constant times the partial pressure of the gas, right? And then we have already discussed the partial pressure over here. KH is the Henry's constant, and Henry's constant is specific to the situation that we find ourselves in. It's not like it's a constant, so it is the same everywhere we go. It differs depending on the type of gas we are having, the solution, and then all of that. Now, it is due to this law of partial pressure that is how also oxygen gets into the blood. When you take the lungs, let me branch off into biology a little bit. It will help somebody if maybe they pay attention. When you take the lungs, at the basic unit of the lungs, there are sacs, tiny air bubble sacs called the alveoli. Now you have the alveoli like this, and this alveoli is innervated with capillaries, right? And then arterioles, or however we call them, or let's call veins and capillaries. You have, let's say, your veins, and then let's say your capillaries over here too, innervating this alveoli over here. Now inside the alveoli, PA, which is the partial pressure of oxygen inside the alveoli over here, is around 100 millimeters of mercury, right? And then the partial pressure of CO2 is around 40 millimeters of mercury in the alveoli. So there are more pressure of oxygen than there are more pressure of carbon dioxide in the alveoli. Let's take the vessel which is supplying the oxygenated blood, taking it from the heart to that would be like a capillary. Let's take a capillary that supplies the deoxygenated blood. When you take that capillary, the partial pressure of carbon dioxide over here is 100 millimeters of mercury. And if you take the whatever which is supplying the heart with oxygenated blood, the partial pressure of oxygen is 40 millimeters of mercury over here. So since the partial pressure of oxygen is bigger than over here, oxygen will diffuse from the alveoli into this, because it will move from a region of higher concentration to a region of lower concentration until equilibrium is attained, and it will get to the this region by making this go up to 100, so the equilibrium is attained, and this is the oxygenated blood going to the heart to be pumped to the body, and the deoxygenated blood coming into the alveoli over here from the heart has a partial pressure of carbon dioxide of 100, but the partial pressure of carbon dioxide in the alveoli is 40. So the carbon dioxide will diffuse from here into here to also attain equilibrium, and then you breathe that carbon dioxide out. So that is how a little bit of look into biology over there, cause of Mr. Henry's law. So Mr. Henry's law is this: the the solubility or the concentration of a gas is equal to Henry's pressure times the partial pressure. It's as simple as that. So from Mr. Henry, we can move on to the kinetic molecular theory of gases. Abib, can you pause it? Ready? All right. So we have reached the point of the kinetic molecular theory. A lot of theories we're dealing with in chemistry. So the kinetic molecular theory, as we said earlier, the ideal gas laws, all these laws over here were designed to fabricate or to facilitate gases that are ideal. And the ideal means that the gases almost have negligible volume, do not react, intermolecular force is almost zero, right? But real gases, which is the gas that we are knowing in everyday life, they are not ideal. In fact, they deviate from the ideal situation. So they made this kinetic molecular theory to, describe and then correct some of the assumptions and then the calculations that we would calculational errors that we might encounter when we're calculating for ideal real gas scenario using ideal gas equation. Now over here, what I want you to pay attention to is that memorizing all the facts might not be that much helpful than understanding the concept of how, or the ballpark in which we are working this with. They made 5 assumptions in developing the kinetic molecular theory of gases. So there were assumptions, right? Meaning they're assuming. So the assumption number 1 is that the gas are made up of particles with volumes that are negligible compared to the container volume. So the gas particle volumes, the volume of the individual molecules, are negligible as compared to the volume, which makes sense. That is the first assumption they made. Gas molecule volumes are negligible as compared to container volume. That is assumption 1. Now, the second assumption that they made was that gas atoms or molecules exhibit no intermolecular forces of attraction. So, no intermolecular forces of attraction. The third assumption that they made was that gas particles are in continuous random motion and they are colliding with each other, right? So the continuous random motion / random collision with each other, right? And then the fourth assumption that they made was that every collision between them was elastic. So the collisions are elastic. Now, when we say collisions are elastic in the sense of kinetics, what we are trying to tell you is that momentum and energy is conserved. So if I have a gas which has a mass of 1, right, moving with a speed of 1, the initial speed, like an initial mass, final mass, and then equalize with another gas, right, moving with also a mass, moving with a mass of like a mass and then a volume. If these two combine, let's say this is A, this is B, right? Momentum is conserved in such a way that when you come to the other end of it, you're going to have the same thing, like the same mass, and then the speed that A was moving, and then the same mass, and then speed that B was moving. Now, it might not be that it will be moving with the same speed, but the interchanging of the speed would also make the energy be conserved. Like, let's say if A loses 2 miles per hour of speed, B would gain that 2 miles per hour of speed. So in such case, no energy is actually lost from the system. That is what we call elastic. Both momentum and then the energy are conserved during the collision. Okay, so that was the fourth assumption. The fifth assumption that they made was that the average kinetic energy of the particles is proportional to the absolute thermodynamic temperature of the gas in Kelvin. And it is the same for all gases at a given temperature, irrespective of chemical identity or atomic mass. This is a lengthy process. All that they're trying to talk about is that the average kinetic energy of the gas is directly proportional to the absolute thermodynamic temperature in Kelvin. That's all they're trying to talk about, irrespective of the gas identity. It doesn't matter whether it is helium, just helium, or cyclopropane, which could also be a gas. The same exact thing. Okay, so once that we have our assumptions taken down, the first thing that we're going to tackle is over here. That is in our best interest for the purposes of the MCAT, the average kinetic energy. We know that the kinetic energy of a particle is equal to the mass of the particle times the velocity squared, right? But when we're saying that the average kinetic energy is proportional to the absolute thermodynamic temperature, so we can get that if we don't want to work with the mass or the volume and we just want to put temperature over there, the equation becomes Ke, which is the kinetic energy, equals to 3 over 2. 3 over 2, 3 thirds, 3 second. Kb, temperature. Now, what is this Kb? This Kb over here is the Boltzmann constant of proportionality, right? A Boltzmann constant of proportionality. This guy called Luigi, I don't know whether the name was French or Italian or whatever. Luigi Boltzmann also involved himself with the gases back in the 80s or something like that, and then he did the experiment to conduct the relationship between the kinetic energy of the gases and then the temperature, and then he came out with this the formula. This formula is really important to me. I will put this in my head because most people already know this. Half is equals K is equals to half mv squared, but not a lot of us know that 32 kb is constant is equals to T. And then the Boltzmann constant of proportionality, Kb, for that, it is always constant. It's not like the Henry's constant. Here the Henry's one, which is the A, is equals to Henry's constant times PA. This Henry's constant changes as conditions changes, but then the Boltzmann constant of proportionality does not changes, and then this 1.38 times 10 raises to the power of negative 23. Wow. Joules per temperature, joules per Kelvin over here. And that is the Boltzmann's proportionality. Now, it makes sense because if you put this unit over here, pay attention. If you put this unit over here, it is going to be a little bit of dimensional analysis over here. It's going to be joules over Kelvin times temperature, which is also measured in Kelvin. Kelvin will cancel Kelvin and we'll finally end with joules. Energy is measured in joules. Dimensional analysis. Make sure you are right over there. Okay, now since that is covered, we will move on to the one assumption that we did make, that the gases are moving at random and then the collisions are also random. So in this case, how do we determine the speed of a particle if it's moving at random? Much more like the Heisenberg uncertainty principle, which I'm just making a reference here. It's not the same thing. You cannot determine the speed.
I needed to cough. I'm sorry, baby. I'm so sorry.
Okay. You cannot determine the speed and then the position at the same time, right? It's similar over here. Over here, since the particles are moving so much random, we cannot calculate the speed of individual particles. So scientists came up with a way to find the speed of the particles combined. And the speed of the particles combined, they call it the root mean square speed. Damn. The root mean square speed. So they usually use U root mean square. They usually use this to represent the root mean square speed of the particles, and is given by the formula RT divided by the molar mass. Right? So this R, this R over here is the gas constant. And what did we say the gas constant was? It could be 8.2 times 10 raised to the power negative 2 liters of atmospheres divided by Kelvin of mole. It's a lot. Or it could be 3.1 joules per Kelvin of moles. Could be any of these things, right? Depending on your units or what you are working with. So that is the root mean square. And this this root mean square just means the speed, right? The speed of the individual gas particles. It's the average speed. That is why we call it the mean. So it is the average speed of the individual gas particles moving around speed. And then over here brings us to the Graham's law of diffusion and effusion. Diffusion and effusion. So diffusion is basically the movement of particles, right? From a region where they are really concentrated to a region where they are less concentrated through a medium such as water, such as gas, such as vacuum, whatever, through a medium. That is diffusion. Effusion, on the other hand, I know you've probably heard this word pulmonary effusion, or we have to do something effusion for the patient. What is effusion? Now, effusion is the movement of gas particles through a tiny hole. So let's say if you have a canister over here, right? And then you have a disc between, then there is a hole in the disc, and then there is a gas up here. Moving the gas through this hole to this chamber is called effusion. Now, if you have this same canister and then the gas move from this place and spread all the way out like that, that is called diffusion. So that is the difference. The Graham's law of diffusion or effusion just did that the bigger the particles, the slower it moves, and the smaller the particles, the faster it moves. Would that be confusing? That if you are big, you can move fast enough, and if you are small and skinny, you can move fast? Isn't that common sense? That is what Graham said over here. Does he deserve a Nobel Prize for that? Well, hello.
You need a PR team, a public relationship team, because you can't. Okay.
Yeah. So that was the rate of diffusion that Graham, the Graham's law state. But then the Graham law, it came with, see, like I said, the bigger the particle, the slower it moves. And then the lighter the particles, the faster it moves. So, and how do we determine how big a particle is, a gas particle is? By the molar mass. So the rate of diffusion, right, is inversely proportional to the square root of the molar mass. So the rate, talking about Graham, Mr. Graham, a guy that invented the telephone, they call him Graham Dell. It's not the same Graham. Since there was a lot of Grahams in science, maybe I should change my name to Graham. Okay, so he said that the rate of diffusion is inversely proportional to the square root of the molar mass. Same thing is the calculation we were doing at first. If we decide to go, we're going to have R1 over R2 equals to square root of M2 over M1. Right? How do we get here? We could do the calculations. Let's do it. So if you want to change the proportionality sign, it's going to be R equals K1 over the molar mass. If I have two gases, I could say K equals to R root of molar mass over here. So this is R1, M1. If I have two gases, K2 would be R2 equals square root of molar mass 2. Like this. If I want to equate them both, it's going to be R1 root of molar mass 1 equals to R2 root of molar mass 2. Like this. And if I want to rewrite it just as this, say I divide here by R2. I divide here by R2. R2 cancels R2. I have R1 over M1 divided by R2 equals to root of M2. And then over here, I multiply 1 over root of M1. And then I multiply 1 over root of M1 over here. 1 over root of M1 cancels 1 over root of M1. So I have R1 over R2 gives me root of M2 divided by root of M1. Isn't it the same as that? Yes. So these calculations are, redundant and mundane. So we don't really put it. So once we state the law, we just write the formula. But the formula came from this calculation, this redundant algebraic calculation over here. Now, let's move on to the last concept, and then we could be done with this. I really did this in one shoot. That's good. That's good.
1 hour though.
Yeah, if they need be, I'll cut the video into two and post them part one, part two, but it's the same video. Yes, a whole movie. Damn. Who is gonna sit and watch an hour of lecture?
Somebody who needs it must feel like they fell in the MCAT the second time.
Somebody who wanna pass the MCAT. Yeah. Okay. Let's talk about real gases. All we've been dealing about were fake gases. My bad. Ideal gases. Okay. So let's talk about real gases. Real gases over here deviates from the ideal situation. How do they deviate from the ideal situation? You have to take them state function by state function. Now, how do they deviate with respect to pressure? So, if you have a gas, right, under ideal situations, if you compress it, you can compress the gas to the point that the gas has no more volume because they say the particles, the volume is almost negligible. But under real situations, if you have a gas and you compress it so much, the gas turns into liquid. So under pressure, right? Under pressure, if the real gas is under high pressure, the gas will turn into liquid. If it's under high pressure, it turns into liquid. That is the diffusion from pressure. Now let's see the deviation from temperature. Okay, so also it's similar that under temperature, right? Under temperature, if you lower the temperature, you get close to the condensation point because the gases, the speed would reduce and you get close to the condensation point of the gas. So under low temperature, the gas would also turn into liquid. But Mr. Van der Waal decided to come up with an equation. In high school, there was a friend of mine called Van der Waal. I see you, Van der Waal. I see you. Do you remember? You will not even solve the equation for us, Van der Waal. Okay. Yeah, Van der Waal catching a fade. Now, Van der Waal tried to incorporate the behavior of real gas into the ideal gas equation. This is the equation he came up with. Look at this monstrosity over here. N squared A all divided by V squared, right? Into bracket V minus N, NB equals to nRT. So this is the monstrosity that Van der Waal did. We have our simple equation over here. Van der Waal, see what you did over here? We have our 9 simple equation over here. Van der Waal took it and decided to make it a monstrosity. P plus N squared A, this is A, divided by V squared into bracket V minus NB equals nRT. So according to Van der Waal, he said that if this gas is real, you can use this equation to calculate for whatever factors or variables you need under real conditions. So the thing is that we have to solve more equations or more work examples with this equation over here, else I don't think anybody could just have it impulsively on their mind until they solve so many examples or keep on reciting the equation every day so it sticks. Okay, people, this right here will bring us to the end of the gas phase. I'm glad that I did it in one take. Watch this video, like, comments, suggestions, anything, put it in the comment section. Thank you and see you in the next video. Amen.